Let's see the topic of integration. The calculus deals with various topics like derivatives, integration, etc. Now, in the first year of the syllabus, we have learnt about differentiation, continued with integration, followed as reverse process of differentiation. So sometimes integration is understood as reverse process of differentiation. So let's recap the derivative, what we have learnt in the previous sessions. Say for example, the derivative which we generally denote by d by dx of x squared by 2 is half d by dx of x squared, that is half d by dx of x squared, which is 2x, which on simplification gives x. Therefore, I understand the derivative of the function x squared by 2 is nothing but x. Is how we understand the differentiation of a function as simplified with the respective formulae. Now, what do we understand with integration as reverse process of differentiation? So, differentiation of this function is this. So, integration of this function would be this. That is, if I take integration of this function x is nothing but x squared by 2 is how we reverse process of understanding. Therefore, it comes to the general conclusion that d by dx of f of x, say, is the function g of x, then that implies integration of the function g of x is f of x, is how we understand the relation between derivation and integration. Integration is the reverse process of derivation. That is, d by dx of f of x is g of x implies integration of g of x is f of x. Therefore, d by dx of x squared by 2 is x implies integration of x is x squared by 2. The integration is anti-differentiation. So integration is anti-differentiation, is how we conclude with the understanding of integration as reverse process of differentiation. So let's define the antiderivative of the function. That is, if f dash x is some f of x, that implies f is called derivative of capital F, and this f is called antiderivative or primitive of f, is how we understand the antiderivative of the function. For this, f is derivative of capital F and capital F is primitive of small f. Say for example, derivative of sin x is cos x, that implies antiderivative of cos x is sin x, is how we understand. Derivative of sin x is cos x and antiderivative of cos x is sin x, is how we understand the derivative and the antiderivative connected with the reverse process. antiderivative is also called primitive of the function. Next is indefinite integral. Now, the concept of indefinite integral is from where the actual integration topic starts in the syllabus. So, what is indefinite integral? As we know that derivative of, say, x square is 2x, then the derivative is written as d by dx is how we write for this. That implies my integration, which is generally denoted by elongated s or summation s, is the symbol for integration. So as I denote the derivative with d by dx, my integration is denoted with integration, that is this of some function f of x dx is how I denote the integration. That is, if I write integral of this is read as integration f of x dx is how I read this. Therefore, when I write the function which is being integrated with respect to x, where f is called the integrand and x is called variable of integration, because this is the variable through which I am going to integrate of integration is how we understand the notation integral f of x dx. Now let's come back to understanding that if I write d by dx of x squared is 2x, then my integral of this is said to be x squared plus c. Now every function is denoted with plus c, which we're going to see in the later session on why the constant of integration needs to be included. Here c is called constant of integration, which we are going to see out there. So therefore, indefinite integral is denoted by integral of f of x dx, read as integration fx dx, where f of x is the function which is being integrated with respect to the variable x, and f is the integrand, x is the variable of integration, is how we understand. Now, as we take the integral of the function f of x dx is taken to be some function with always c which is attached. This is how the formula is taken. But the biggest question here is, why do we need to put plus c for every indefinite integral which is taken into consideration? For indefinite integral, indefinite integration, I have integral f of x dx is f of x plus c, where c is constant of integration. C is called the constant of integration. The reason for inclusion of c is, if you go back to anti-differentiation concept, I have d by dx of x is 1, or x squared by 2 is x. Say d by dx of x squared by 2 we know is x. That implies integration of x is x squared by 2, because these are anti-differentiation. So integration of this is this, because derivative of this is this. Similarly, if I take d by dx of x squared by 2 plus 2, so this also implies that integration on the right side is equal to the anti-differentiation, that is x squared by 2 plus 2. Similarly, if I take d by dx of x squared by 2 minus 3, and let's see what will be its derivative on the right. So this gives me x minus d by dx of minus 3, which is 0, which is also x, which I get here. That implies my integral x dx can also be written as x squared by 2 minus 3. So I get this to be this. Therefore, concluding, I get d by dx of x squared by 2 minus any constant I include here gives me the value as x. Therefore, integral of x dx is x squared by 2 or plus c is what I get. So this makes us understand that irrespective of whatever is the constant, the derivative of a function always has been the same. Therefore, the integration of this will be plus c, which always comes as the constant of integration. There is some constant which is missing in the antiderivative concept, which is included in every definite integral. So plus c is a must in every problem, because derivative of this is this also is this, and of this also is this. In general, of this function is also x. Therefore, integration of f of x dx is f of x plus c. C is the constant of integration. So now that we have understood the integration as the anti-differentiation, let's take a special case to connect differentiation with integration. That is, if I want to find integral of d by dx of this over dx, then clearly I find that since integration and derivative are anti to each other, they get nullified. In general, I say these two get nullified, which gives us f of x plus c. So integral of derivative is f of x plus c is how we understand integration connected with derivative as nullifying or cancelling each other to give f of x plus c. For example, integral of derivative of this dx will be x squared plus c, because derivative and integration cancel to give the function itself plus c, the constant of integration. Now there are some standard formulae which we must remember in case of integration, just like the standard formulae in derivatives. So for some standard functions, let's see how we can memorize the integration formulae. To start with, integral of x power n is x power n plus 1 by n plus 1 plus c. Now in this case, we assume x as all real numbers, though I do not mention, it is generally assumed that x is set of all real numbers, or x belongs to R. So integral x power n dx is always equals x power n plus 1 by n plus 1 plus c, and of course n is not equal to minus 1, because if n is equal to 1, this becomes minus 1, then the denominator becomes 0 and hence undefined. So for n not equal to minus 1, x power n dx is this plus c. If suppose my n is equal to minus 1, let's see what the formula reduces to. Then this is nothing but written as 1 by x dx, which is log x plus c, is how we understand the concept of integration. Integral a power x dx and of course plus c. The difference is this is exponential and this is general a, for which I get this assumed that a is greater than 0, because for a negative log is not defined, so I take a greater than 0 and a is not equal to 1. So using this we get the formula for e power x and a power x with plus c out here. Now next is integral of sin x, which is minus cos x plus c. Now here we always have, when there's an integration, there is a derivative also equally attached. So whenever I write integral of some function, then I get d of x, which are very much related to each other. So integration and d of x are very much associated, because whenever I write an integration, I write equally d of x here out there. Next, my integral of cos x is sin x plus c. And then next I have integral of tan x which is log mod secant x plus c. And then comes the next formula continued from the session. Next is integral secant square x, which is tan x plus c. And then integral of cosecant square x, which is minus cot x plus c. And then integral secant x tan x, which is secant x plus c. And then I have cosecant x cot x, which is minus cosecant x plus c, is how we have the trigonometric integration formula. And then I have integral 1 by x, which is taken as log x plus c, and integral log x x if this is assumed with base a. Integral log x is x into log x minus 1 of dx, is how we get the list of formulae in connected with the standard functions. Now continued, we have integral tan x is log mod secant x and plus c, and integral cot x is log mod cosecant minus cot plus c, and integral tan x is log mod secant x plus tan x plus c. And then I have integral cosecant x is log mod sin x, integral secant x is log mod plus c. And then we have integral 1 by root 1 minus x squared, and of course x is assumed to be outside 1 and minus 1. We don't have the value outside of 1 and minus 1, so x is between 1 and minus 1. So with this I get this as sine inverse x plus c. And integral minus 1 by root 1 minus x squared of dx is cos inverse plus 6. So if I have 1 by root, it is sine inverse, and minus 1 by root this is cos inverse. To be continued with the rest of the formulae in the session. Next, if I want to find integral of 1 by 1 plus x squared dx, then this is tan inverse x plus 6. Or if I want to find integral of minus 1 by 1 plus x squared dx, this is cot inverse x plus c. And then if I want to find integral of 1 by mod x root x squared minus 1 of dx, then this would be secant inverse x plus c. And similarly, if I want to find integral of minus 1 by mod x root x squared minus 1, this is minus cosecant inverse plus 6, assuming x is greater than 0. So this is how we get the values which are between 0 and 1, assuming on the domain to be restricted based on root and mod. Is how we get the formula. Now let's see the integration of some hyperbolic functions. So integration of hyperbolic functions. So we're going to find few of the integration of the hyperbolic functions in this session. Say I have the hyperbolic function sine hx. We know that the hyperbolic functions are with the respective formulae. So integral of sine hx dx is given by minus cos hx plus c, is how we identify. And integral of cos hx dx is minus sine hx plus c. Similarly, if I want to find integral of secant square hx dx, then this is nothing but tan hx plus c. And cosecant h square dx is given by minus cot hx plus c. And then I have integral secant hx tan hx dx is given by minus secant hx plus c. And then integral of cosecant hx cot hx dx is given by minus cosecant hx plus c, is how we proceed with various hyperbolic functions. And similarly, if I want to find integral of 1 by root 1 plus x squared dx is given by sine h inverse x, or this is also log x plus root 1 plus x squared. I can use this or this for finding integral, and of course plus constant of integration. Next, integral of 1 by root x squared minus 1 dx is cos h inverse x plus c, or this is log mod x plus root x squared minus 1 of plus c, is how we have various hyperbolic functions with their respective formulae.